and welcome to another college math video. In this video, we're going to continue working probability. We're going to focus on the difference between and or in probability. Our objective for the video, we only have one. Solve applications involving or, and, not any. Let's fix that. And mutually exclusive events. We've seen, or we will see, depending on the order we cover the chapters in the course, the difference between and or in a few other places. So this is just where we're going to focus on it in probability. Okay, so notes. We're going to start with the or scenarios. For any problem that you see, what's the probability of this or this happening? This is a little formula that you can use in all of those cases. I have it pretty spread out here for us to look at. Oh, the words are over me. Sorry about that. But I want to give you the visuals of what this looks like, just so you can see it. Remember, in sets, this is what A or B looked like, and we know what each one individually looks like. A, B. You're not going to be asked to draw these pictures anywhere, at least in this chapter. I just want to give you the visual of, if we're looking for the probability of this or this, so this stuff, where does it come from? The formula is, well, if we get the probability of one of those two things happening and add it to the probability of the other of those two things happening, we then have to subtract out the probability that both of them occurred. And why do you think that's the case? Well, if we just added these two together, then we will have double counted for the stuff in the overlap. So we subtract it out one time. So the formula I'm going to list one more time, a little bit more concise. Looks like this. Notice there is an and in here, but there's one event happening. So this is just multiple criteria. We're looking for A or B being the thing that occurs. Okay, another note we have is on the mutually exclusive, which is a special case. And this is when it's impossible for both events to happen simultaneously. So the good news is that the formula will always work. The mutually exclusive would be the case where the two circles have absolutely nothing in common. And so you can use this formula, chunk of A plus chunk of B, and subtract out what they have in common. Because there's nothing they have in common, you'll just be subtracting out 0. So there is this special mutually exclusive case, but you don't really have to worry about it because it's always just going to be embedded in the potentials for the problems like this. All right, so there's our formula. One other special note, this is for all of the OR questions, and I cannot stress how important this is for all of these OR questions. In all of these, there is only one event happening. It's one event, and A and B are just different criteria within that event. So we're pulling one card. What's the probability that it's a 7 or a 10? What's the probability that it's a jack or a red? There's still only one pull of the card, but we're looking at multiple criteria possible. So anytime we have an OR question, there can only be one event happening. So let's see some OR examples. All right, so let's say we have one card chosen from the standard deck of cards. Again, if you don't remember the standard deck offhand, you can pull it up on another tab to look at right now. But long term, that should be something that you're familiar with. Find the probability of choosing a 7 or an ace. So let's say you're playing a card game, the whole deck exists, and the thing that you need to win is either a 7 or an ace. For whatever reason, those are the cards that would cause you to win the game. So we can think about this two ways. The first is using the formula. We can think of the first piece, the 7, as your event A, and the second thing, the ace, as your event B. So the formula says we want the probability of choosing a 7 plus the probability of choosing an ace, and then we'll subtract out anytime it's a 7 and an ace. So probability of choosing a 7. Remember, in the full deck, there are 52 cards. Out of the 52, 4 of them are 7s, one from each suit. For an ace, Again, 52 cards, 4 of them meet the criteria. And then how many cards individually are both 7 and ace? Single card meets both criteria. Still out of 52, out of the whole deck, none of the cards are both a 7 and ace. Those are two totally separate things. You won't find any that are 7 or ace. You could find some that are 7 and red, which would be a different problem. But this one's 7 and ace, so there are none in common. This is what we simplify. You can do it by hand or in the calculator. Remember, you can type all of this in, then hit the math key. The first option says change to fraction, and then hit enter. And it'll give you the simplified answer. 8 over 52 simplifies to 2 over 13. This is an example of a mutually exclusive case. A card cannot be both a 7 and an ace. And so the formula still works because you'll just be subtracting out 0 over 52. Let's do one more in this realm just so that we can see. Actually, the next problem is going to embed that, so that's all right. Okay, so let's say you roll a 6-sided die. There's one roll happening. There's only one event. Find the probability of rolling an even number or a number greater than 3. So the events are even number, we'll call that E, or number greater than 3. I'm just going to call that G. We can use the formula, probability of even or greater than 3, which says probability of even plus probability of greater than 3, and subtract out any that are even and greater than 3, the ones that we've double counted for. Okay, so what's the probability on your one roll that it's even? There are 6 options. Of those 6, how many meet the criteria of being even? 3 of them, 2, 4, 6. How many of them are greater than 3? Still out of 6. Greater than 3 could be 4, 5, 6. So again, we have 3. And then subtract out of the 6 those that meet both criteria. It's still one event. This is just how we come up with this individual probability. Even and greater than 3. So greater than 3, 4, 5, 6, even 4 and 6 meet that criteria. So 2 here. We've already accounted for 4 in both areas, so we have to subtract it out once. All right, so simplify this. 3 plus 3 minus 2 is 4 over 6. Simplifies to 2/3. And that's our final answer. Now, in both of these cases, I used the formula. You don't necessarily have to use the formula. You can think through the problem a different way. So let's go with the second example, because this one's a little bit easier to visualize. Our options are 1, 2, 3, 4, 5, 6. Those are the options. Of the 6, how many are going to meet our criteria? So we want even or a number greater than 3. So I'm just going to circle all of those that meet either one of the 2 criteria. Even and greater than 3, just greater than 3, even greater than 3. So how many of the 6 meet our criteria of even or greater than 3? 4 out of the 6, which simplifies to 2/3. So either way, we get the same answer. Which way is preferred? It's really up to you. In the case of something small, like rolling a 6-sided die, where you can physically list each option and then just circle which ones work, sometimes that's easier. But for something like the problem above, one card is chosen randomly, you don't really want to have to list the entire deck of cards. If you can look at the entire deck and then just count how many meet the criteria, that'll work as well. So if you did it that way, of the 52, if you looked at the full deck of cards, you would count 4 that were 7s, 4 that were aces. None of them were the same, so you would just have those 8 total, and then it would simplify to the same thing. Now, again, that's a mutually exclusive, so maybe a little bit easier to do in your head, but it can get more complex if the criteria overlapped somewhere. It's hard to visualize the entire deck and then count from the entire deck if there are 52 options, which in the deck of cards there are. So both options completely work. You can use either one wherever you see fit. All right, a couple more examples together in this realm. When a student goes to the study abroad office, the probability he or she has a question about global distinction is 0.6. Global Distinction's a program we offer here at Valencia. You're actually getting credit for a global distinction class by taking this class. You can ask me questions about it if you're interested. The probability that it's a study abroad question is 0.1. The probability that it's a global distinction question and a study abroad question is 0.05. Find the probability the student comes in with a question about study abroad or global distinction. So this is an or scenario again. Study abroad, we'll call S. Global distinction, we'll call G. All right, probability of S or G. This one is the case where you're stuck using the formula if you're given these specific pieces of information. And they're giving us decimals, so we're going to present a decimal answer. For the most part, your answers are going to be fractions. Okay, so the formula says take the probability of each individual piece and add them together. Study abroad only, global distinction only, and subtract out if it's both study abroad and global distinction. And we have 3 of these pieces of information. We were given the probability here, she has a question about global distinction, is 0.6. The probability it's about study abroad is 0.1. And the probability that it's both global distinction and study abroad is 0.05. And we're looking for the probability that it's one or the other. We're looking for this number. So we have all the information we need. Just simplify probability study abroad or global distinction. 0.1 plus 0.6, 0.7 minus 0.05, 0.65. And then anyone else going in is asking a different question. All right, one more question in this realm. Find the probability of A or B if probability of A is 0.8, probability of B is 0.6, and probability of A and B, it being both of the things, is 0.5. Again, this one's a formula question. You could use Venn diagrams if you wanted to, but I wouldn't suggest it, but it can be done that way. So remember, this is the formula. Just plug in each individual piece. Probability of A is 0.8, B is 0.6, and both A and B, both criteria, is 0.5. 0.8 plus 0.6, 1.4 minus 0.5 is 0.9. So the probability that it's A or B, either one of those 2 criteria, is 0.9. These 2 types of questions you'll see less often than the first 2 that we saw. All right, so let's do a little practice. These are all or scenarios. You roll a 12-sided die. The options are 1 through 12. There it is. Find the probability of multiple of 3 or even, less than 3 or greater than or equal to 10, even or multiple of 5, and then one more at the bottom using the formula like we just did. So go ahead and pause the video, go through these problems, and we will see if we're on the same page in a moment. Okay. All right, so let's go through these problems, and we're going to go through them both ways because in this case we have options of 1 through 12. So we can physically list all of them out without going crazy. Let's do formula first. Probability of multiple of 3 or even. Probability of multiple of 3 plus even minus probability of multiple of 3 and even. Okay, so multiple of 3. Actually, let's do it on the side. Multiple of 3, 3, 6, 9, 12. So of the 12, there were 4 that met the criteria. Probability of even. There are 12 options. How many of the 12 are even? 2, 4, 6, 8, 10, 12. So 6 of them. And then subtract out which of the 12 are both a multiple of 3 and even. Our multiples of 3 were 3, no, not even. 6, that one is. 9, not even, and 12. So 2 of the 12 are both a multiple of 3 and even. Simplify. 4 plus 6 is 10, minus 2 is 8 over 12. And this simplifies to 2/3. An alternate way of doing this problem without the formula is to just look at all the options. This one will be in red. And we'll just underline which meet either one of the two criteria. Could be one, could be the other, could be both. We want multiple of 3 or even. So here's even, multiple of 3, even, both, even, multiple of 3, even, and both. And then how many of the 12 meet either or criteria? 1, 2, 3, 4, 5, 6, 7, 8 of the 12 simplifies to 2/3. I'm not saying you have to use the formula. You can pick one way and stick with it. All right, second problem, we want probability of less than 3 or greater than or equal to 10. I'll just use these two symbols. So it's probability of the first thing plus probability of the second thing minus probability of both of them. So probability of less than 3 out of the 12, how many meet that criteria? There are only 2, 1 and 2 are less than 3. Plus of the 12, how many are greater than or equal to 10? We have 10, 11, and 12. So 3 of them. And then how many meet both criteria? Less than 3 and greater than or equal to 10. Trick question, there are none. Not a trick question, that might be what it takes to win the game. And there are none that meet those. This is the mutually exclusive case. It will not ever be both of them, but you can still use the formula. Add them up, we get 5 over 12. It doesn't simplify, so that's as good as it gets. The alternate way is to look at your 12 options and just count how many meet either criteria. So of the 12, we have less than 3, greater than or equal to 10. Less than 3 are these two, greater than or equal to 10 are these 3. So how many have an orange squiggle? 1, 2, 3, 4, 5 out of the 12. You've got your answer. I would encourage you to be comfortable doing it either way. Like I said, there's only 12 options here, so it's easy for us to look at all possible options and just count, but it gets a little bit more difficult when there's more options. Okay, the next one, probability of even or multiple of 5. We'll call it even for E for even and M for multiple of 5. So the formula says probability of even plus probability of multiple of 5. Oops. Minus probability of even and multiple of 5. So plug them in. Let's go underneath here. Probability of even of the 12, still the 12-sided die. How many are even? There are 6, 2, 4, 6, 8, 10, 12. Multiple of 5 of the 12, how many are multiples of 5? 5 and 10, so 2. And how many are both even and a multiple of 5? Multiples of 5 were 5 and 10, and only one of those is even. So there's only one that is both even and a multiple of 5. Okay, pull it all together. 6, 7, 8 minus 1 is 7 over 12. And one more time, the alternate way. Look at your list of options, and this time I will do a line above for each that are even or multiple of 5. Here's even, multiple of 5, even, and multiple of 5, even. And then just count. We have 1, 2, 3, 4, 5, 6, 7 with a yellow squiggle above out of the 12. Either way totally works. Okay, and then the second problem, find the probability of A or B if probability of A and B is 0.2, probability of A is 0.52, and probability of B is 0.61. This one's straight formula. There's really not another option unless you want to draw Venn diagrams, but I don't think it's worth it. We know the formula is probability of A plus probability of B minus probability of A and B. So probability of A is 0.52 plus probability of B 0.61 minus A and B 0.2. You can do that in the calculator. We get 0.93. All right. So again, to summarize on these OR problems, there's only one event. One event. Now let's take a look at the AND problems. Okay, so for and we have another formula. I'm using a capital A and D in these cases. I should have listed it there as capital, but it doesn't really need to be. The distinction is between how many events are happening. In every OR scenario, there's only one event. For the AND scenarios, in this section in particular, will all be more than one event, but sometimes you'll have to make that distinction for yourself. If there's only one event happening, it's all about criteria. If there's more than one event, then it's more than one probability. So this is the formula. If it's probability of A and B, you just multiply each probability by each other individually. So find probability of A, find probability of B, multiply, and that's your overall probability. This could get bigger if there's more than two events. Let me just note. If there were 3, it would be probability of A times probability of B times probability of C. It just keeps going. For however many events, you're just multiplying each probability individually. And these are the important things to keep in mind. It requires a favorable outcome in each event. We assume that event A happened when calculating the probability of B. And this means that event A happens, then event B. So whatever it's listed, A and B, it's that thing first, and then B, and then potentially C, and then D, just each one individually. So for these AND problems, this is the big thing to keep in mind. This only works, this formula, if there's more than one event. Those OR questions only had one event. It was just criteria that we looked at and kind of dissected it. Here, it's more than one event. And since we have more than one event, there's 2 ways that we can break this down, because in some cases, let's say we're pulling cards from the deck, it matters if the card is put back or not. So we're going to distinguish and separate even further to look at 2 things, with and without replacement. So first, we're going to focus on with replacement. So in the card example, I mean, we picked a card, and then we put it back, shuffle, pick again, and then we'll distinguish between without replacement. All right, so let's start with a simple example. There is a bag with 1 croissant, 1 macaroon, and 1 eclair. These are popular French desserts. You make 2 selections. 2 selections, this tells you 2 events. Find the probability of first choosing a macaron and then choosing an eclair. 2 events. So probability of macaron, probability of eclair. 2 separate events. So we find each individual probability. So probability of choosing a macaron. There's 3 options in the bag. Of the 3, how many meet the criteria of being macaroon, what we want? There's only 1. Okay, so we assume we picked it, and then it gets put back in the bag. Shuffle, shuffle, shuffle. Now what's the probability of choosing an eclair? Again, there are 3 options. Of the 3, only 1 is an eclair. So you have each one individually. Now multiply. You can do this, you can do it on the calculator. If you're wanting to type in the entire fractions, the whole thing all at once, I would suggest putting parentheses around each individual fraction, or you can just multiply straight across on top. 1 times 1 is 1, and straight across on the bottom, 3 times 3 is 9. So if you're making 2 selections, there's a 1 in 9 chance that you would first choose a macaroon and then choose an eclair. This is with replacement. Let's see another with replacement. 2 cards are being selected. Wow, I'm sorry that the words are on my face again. 2 cards are selected, 1 at a time, with replacement from the standard deck of cards. If the information is needed, the problem will tell you if there is replacement or not. So this one says with replacement. We know the card is picked, and then it's put back. So what's the probability of choosing 2 jacks? So probability of jack and jack is probability of choosing a jack times probability of choosing a jack. Each individual thing multiplied by each other. So what's the probability of choosing a jack? There are 52 cards in the deck. How many of the 52 meet the criteria of being a jack? There are 4, 1 in each suit. Okay, we've chosen, we assume that we picked a jack. That's how we get to keep playing, but there's replacement, so we put the card back. And then we make another selection. On our second choice, All 52 cards are still an option because we put the card back. And of the 52, how many are jacks? Still 4 because we put the card back. You can simplify first or simplify later. It's up to you. I'm just going to do both at the same time. We get 1 over 169. Each of these simplifies to 1 over 13. 1 over 13, 1 over 13 multiplies, so you have 1 over 169. We will distinguish between without replacement a little later in the video. Okay, let's say 3 cards are selected in the next example, one at a time, with replacement from the standard deck of cards. Find the probability of choosing a heart and a diamond and a heart. Now, the word then isn't in there, but I think it's helpful when you know that there's more than one event to kind of add the word then in there for yourself. You're choosing a heart and then a diamond and then a heart. And we are putting the cards back every time. Heart, diamond, heart. Okay, so what's the probability that we choose a heart? Of the 52 cards, how many are hearts? Think about the full deck. 13 of the 52, or 1/4, you could simplify it, are hearts. Okay, so we've chosen it. It was a heart. We get to keep playing. We put the card back in because it says with replacement. Shuffle, shuffle, shuffle. Next selection. There are 52 choices still because the whole deck is existing. How many of them are diamonds? Again, 13 of the 52, or you can write 1/4. Okay, we picked a diamond. We get to keep playing. Put it back in. Shuffle. On the third selection, we have 52 choices. How many of the 52 are hearts? Again, 13 or 1/4. Then multiply to get your answer. Each of them is 1/4. So 1 over 64. 1 out of 64 times when you pulled 3 cards one at a time, would you expect to get a heart and then a diamond and then a heart? That's what this says. In these problems, the denominators typically end up blowing up because it becomes harder and harder for these things to occur. But that's how you would find it. All right, let's distinguish between without replacement before we do some practice problems. This is with replacement. Every time the card was put back, or the items were put back. Without replacement, let's do the same scenario we started with. 2 cards selected. Find the probability of choosing 2 jacks. So probability of a jack and then a jack. Okay, so on our first selection, all 52 cards exist. How many of those 52 are jacks? 4 of them are. Now, the question does not say without replacement because I have the header up top here that we are under the umbrella of without replacement. But the question would have to tell you in this case if there was or wasn't replacement. For a deck of cards, they have to let you know. Okay, so on our second choice, there's no replacement. The jack is out. Remember those notes from the beginning of this little area. We assume that the thing happened, so we got a jack. How many cards are left now? There were 52, but we're still holding one. So on our second choice, how many cards are left? Only 51. And then of those 51, how many are jacks? We have to assume that the first thing happened, which was a jack. So now there are only 3 jacks. It's not always as simple as just subtract 1 from exactly what you see here. It was in this case because this was the same event, a jack and then a jack. You just have to analyze independently each time. All right, so we'll simplify. We get, if you multiply straight across, 12 over 2652. That simplifies to 1 over 221. There is no better way to think of this. Essentially, if you wanted to try to draw this one out, you would be drawing out 2,652 different options and then circling all that met the criteria. You don't want to do that. If it's more than one event, just use the formula. You're just multiplying lots of individual probabilities. Okay. Next one, let's say we have some chips in a bag. There are 4 blue, 9 yellow, 8 purple, and 3 green. They're all shuffled around in a bag we can't see. And we're going to choose 2 chips randomly. Again, the directions would have to say without replacement. We are under this umbrella right now, so I'm not adding it in there just to save space, but it will say that for you on problems. So what's the probability that we choose a green and a blue, meaning we choose a green and then we choose a blue? So probability of green times probability of blue. And they're happening in this order. That was our other special note. So what's the probability of choosing green? First, how many chips are there in the bag? 4 plus 9, 13, plus 8, 21, plus 3, 24. So of the 24, how many meet the criteria of being green? 8. Okay, this is without replacement, so we keep the green chip and we make our second choice. Now how many chips are there? 23, because there's one out of the bag. And then of those 23, how many are blue? We want blue this time. Still all 4 blue chips exist in the bag. We pulled green and we kept green, so there are 4. The first fraction to come up with is always the easiest because you have all possibilities still existing. The second one, especially under the umbrella of without replacement, is where you really have to focus in. Your denominator is probably getting smaller because you're keeping things, and then the numerator, it just depends what's already happened. So multiply and then simplify. We get green. Oh, not 8. Sorry, I was looking at purple. Whoops. Out of 24, there are 3 that are green. The same thing still applies, though. We kept the green, so there were only 23, and there were 4 blue. So 12 over 552, which simplifies to 1 over 46. So you have a 1 in 46 chance of choosing green and then a blue. Okay, last scenario with the chips. Let's say 3 are chosen randomly. What's the probability of choosing a purple and then a green and then a purple? We're still under the umbrella of without replacement. So probability of purple, probability of green, probability of purple. Okay, probability of purple. Out of the 24, how many meet this criteria of being purple? There's the 8. My brain was ahead of me. 8 out of the 24 are purple. Okay, we assume it happened. We chose a purple chip. We're keeping it. What's the probability of choosing green now? There aren't 24 chips anymore because we kept one. There are 23. How many of them remaining of those 23 are green? All 3 green still exist, so 3 out of the remaining 23. We keep the purple and green chip that we selected, and now we make a third choice. How many chips are left now? 22, because we still have 2 of them in our hands. And of those 22, how many are purple? Well, there were 8, but we are holding a purple, so there's only 7 left in the bag. You have the probability of each individually. Multiply and simplify. 168 over 12,144, which simplifies to 7 over 506. So you have a 7 out of 506 chance of choosing purple and then green and then purple from a bag of chips with 24 options like that. All right, so let's do some practice. The letters up here, there's no difference in the coloring on the back. It's just the letter. Imagine that these are Scrabble tiles. You have 3 X's, 2 A's, 3 Z's, 4 B's, 2 E's, 1 I, and 1 H. Now, those are what are in the pile. You don't know where they are. They're shuffled. And in each scenario, you're choosing either 2 or 3 randomly. The directions are there if it's with or without replacement. So go ahead, pause the video, go through these problems, and then let's go through them together and see if we're on the same page. Okay, so let's see if you got these right. In the first one, 2 are chosen randomly. We want the probability of B being chosen and then H with replacement. So we're picking, and then we put the tile back in, shuffle, pick again. So probability of B, probability of H. The probability of choosing a B, how many total are there? There are 16 total. Of the 16, how many are a B? 1, 2, 3, 4. We picked a B, and then we put it back in. So on our second selection, we still have 16 choices because there was replacement. Of the 16, how many are an H? Only 1. 4 over 16 times 1 over 16, Multiply and simplify, we get 1 over 64. Okay, same scenario on number 2, but it's without replacement. Probability of B, then H, without replacement. Probability of B. The formula looks the same, but your analysis is a little different. The first one's always still the same. Probability of choosing a B on your first selection, 4 out of 16. There are 16 options, 4 of them meet your criteria. That's it. The second one is where we have to decide. There is no replacement, so we're keeping the B. How many tiles remain? Only 15. And of those 15, how many meet your criteria of being an H? 1 of the 15. Multiply, simplify, we get 1 over 60. You might be wondering, is it just as easy to always subtract 4 in the denominator? No, it just depends on the numbers. Sometimes it happens. Most of the time, it'll be something totally different. Okay, third scenario, 3 are chosen randomly. Find the probability of choosing X, then B, then Z, with replacement. So we're picking and then putting back, picking and then putting back. Probability of X, probability of B, probability of Z. So probability of X, there are 3 of the 16. We picked an X, we get to keep going, we put it back in, shuffle, there are still all 16 available. Of the 16, how many are Bs? We have 4, we picked a B, great, throw it back in, shuffle, and then the third selection of the 16, how many are Zs? 3 of them, multiply, simplify, doesn't clean up too nice, we get 9 over 1024. Okay? Third scenario, 3 chosen randomly, find the probability of X, then B, then Z, which is the same scenario we just had, but now without replacement. I really want to make sure that you see the difference between these two. Analyze each one individually. Probability of X. There's 16 options. How many of those 16 are an X? 3 of them. There's no replacement. Now we're keeping the X. So our next choice, we're looking for a B. There are only 15 left. Of the 15, how many are a B? There are 4. And on our third selection, we're keeping the X and the B that we pulled, so there's only 14 left. How many of them are a Z? And it's 3. Multiply and simplify, we get 3 over 280. Remember, you can do all that in the calculator, and once it gives you the decimal answer, you hit the math button. The first option says arrow fraction, that means change to fraction. Hit enter, and it'll give you the simplified fraction, 3 over 280. And then the last one, 3 chosen randomly, find the probability of X, B, and then X. Oh, I forgot to write it. Without replacement, I apologize. Because you would need to know that. It'd be a different answer either way. So without replacement, which means we are keeping them. There's space, yes. Probability of X, probability of B, probability of X. So probability of X is 3 out of the 16. We're keeping it, so then there's only 15 left. Of the 15, how many meet the criteria of being a B? And there are 4. And then the third selection, there's only 14 remaining. Of the 14, how many are X's? There were 3 to begin with, but we're holding 1 still because there's no replacement. So there's only 2 left. Multiply, simplify, 1 over 140. All right. Okay, so this video was about the distinction between OR and problems. In every OR problem, there's only one event. It's just different criteria that you're looking at to meet for your probability. For and, for the most part, I guess it just depends if it's one event or multiple. If it's multiple events, then you follow the formula we just used. Multiply each individual probability, and then you make the decision based on the problem if there is or isn't replacement, or it'll say, and then you go from there. All right, I'll see you soon for another video.